day, I'm Dr. T and welcome to my whiteboard. Today we're going to be looking at what we call stoichiometry. This is the ability to look at atoms and molecules and basically do chemical accounting to figure out how many molecules will go in and how many molecules will come out. Now keep in mind, we are always governed by conservation of mass, so we're never going to create matter or lose it, but we can start talking about how we're going to rearrange and shuffle our atoms and how much of one compound are we expected to get. Now, most compounds, you measure them in a couple of different ways. The simplest would be simply to weigh them. So I could take, say, 12 grams of methane. A fairly straightforward approach. Yay, I've got 12 grams of methane. And I'd like to know how much oxygen it's going to consume. I can't do 12 to the oxygen because I don't know what kind of ratios they're going to pair up with. So I want to use the balanced chemical equation. So I have myself a balanced chemical equation. This is telling me that for every one methane molecule, it is going to react with 2 oxygen molecules to yield 1 carbon dioxide and 2 waters. But here's the catch. I can't say that I'll need 24 grams of oxygen. The mass of oxygen is different than that of mass of methane. And this is not saying 1 gram to 2 grams. This is saying 1 molecule to 2 molecules. Okay, we need to do some accounting and we're going to need some units. So the unit we typically use as chemists is called the mole. This is 6.022 and some more digits times 10 to the 23rd of a thing. This is known as Avogadro's number, named after Avogadro, who had done some of the early work setting this up and getting the idea. He definitely didn't come up with the final number though. Okay, so we can use our formula weight, effectively the average weight of the molecule, to go from grams to moles. Okay, fairly straightforward. Now, we could use Avogadro's number to go from moles to atoms or molecules. But warning, you almost never want to do this. Moles are large because atoms are tiny. We almost never work in individual atoms. Even though our chemical reaction is expressed in individual atoms, we don't work in that. Just like you could express recipes involving eggs, as in dozens of eggs, if you're going to scale up the recipe, we can say 1 mole of methane reacts with 2 moles of oxygen. Because the mole is a counting number, we can simply swap the 2 in and out interchangeably as long as we stay put in a reasonable approach. Avogadro's number is used to find the number of atom or molecules. This is a very specialized thing. Generally speaking, if you think you need to do this, you've made a mistake. So be absolutely certain that you actually want the number of individual atoms or molecules before ever invoking Avogadro's number, because odds are you won't need it. As a chemist, I basically haven't used it doing chemistry. I always use the mole. I never convert into individual atoms because they're just so small. For reference, that is about as many grains of sand there are on the Earth. That's a lot. Okay, so let's see about actually using this. Now, I'm going to need the formula weights, which I have over here. This is for my methane, that's for my oxygen. You may hear the formula weights referred to as molar mass, molecular weight. These are all, for our purposes, the same thing. And they're basically the sum of all of the individual atomic weights for all of the atoms in the ionic compound, or the formula unit of your ionic compound, or the molecule, which today we have molecules. Okay, so I'm going to take my initial amount of mass that I'm dealing with, so the thing that I know, and I'm going to be using dimensional analysis. So it's what I want divided by what I got, and I'm going to do a couple of steps. So I'm going to start out with what I know, and then what I want by what I got. I'm going to use the formula weight, in this case for the methane. Now, I'm going to use my coefficients from up here, specifically the invisible 1 and the 2 in front of the oxygen, and I'm going to use this as a ratio. I'm saying for every 2 moles of oxygen, I've consumed 1 mole of methane. Now, I'm going to continue on. I'll use the formula weight of the oxygen, because now I'm in oxygen units. I started out with grams of methane, I've gone to moles of methane, I've switched from moles of methane to moles of oxygen, and now I'm converting to grams of oxygen. We usually don't stop in moles because it's impossible, or It's impossible. You can conceive of a way to do it, but you would never succeed. It's impossible to actually count in moles. They're just so big. So instead, we have to do things like count by weight, in which case we're using the formula weights and the masses. And now, I have determined my oxygen. I have 48 grams of oxygen. A couple of quick points I want to make out. First, general motif for the way we're going to be doing a lot of stoichiometry. You're going to be starting out with a unit that you're able to use. Right now we're looking at grams, but there are other units available that you're able to get into moles. You will start out with grams of the first thing you're dealing with, whatever you're starting with. The piece of information you actually know how much you have. Start with grams of that, use the formula weight to get moles of that. Moles are in the middle. They're basically always going to be in the middle for these stoichiometry ones. Never at the ends, and almost never absent. Now, you use the coefficients, the invisible 1 and the 2 in our previous case, or whatever your particular balanced chemical reaction, and it has to be balanced. So check out the video on balancing chemical reactions if you're not sure or not up to speed on that. So we're going to use those coefficients, and you're going to get moles of B. Then you'll convert moles of B into a unit that is useful to you. In this case, we're presuming grams of B, but there are other choices for this. Additionally, let's talk about significant figures. You'll notice I'm starting out with 2 significant figures in my question. Depending on my periodic table, I can get a lot of significant figures for my formula weights. I have pulled 3 from the periodic table for my 2 formula weights. This will be my limiting significant figure. I will have 2 significant figures at the end. I don't have any limitations from these guys. My coefficients, these are exact, so I don't have to worry about that. These are measured numbers. They will affect my significant figures, so I just make sure I pull an extra significant figure from the periodic table. I don't need to go more than that, although there's no real reason not to other than just more writing. So I pull at least 1 more from the periodic table, which in this case, I forgot my point O, but you get the idea. It is a point O from over there. With that said, have a wonderful day.